Okay, so let's get started again. So I'm going to give you a little bit of a whirlwind tour, starting from a database perspective of how you can quantify the Eric Brewer's CAL Theorem and come up with a numerical relationship. And the goal here is not just to do some math, but to actually be able to quantify the trade-offs. So in particular, the ability to specify a quantitative tolerance for inconsistency. Actually, let me turn it around. Let me give you a real use case for this. Okay? Suppose you're designing a system and let's put it in the database context right from the start. Okay, you want your database to be able to respond to users within 30 milliseconds. That's a requirement. You're under contract to deliver a distributed database that does that. Okay. Now the question is, how do you achieve that? And the issue is, of course, you design your system so that from that 30 millisecond requirement, you want to be able to derive what parameters can be consistent with that 30 millisecond requirement. Okay. So obviously, if you require strong consistency across the database, then the 30 milliseconds is going to put a hard bound on network latency. Right? Because of the CAL theorem, and if the network breaks, you have to give up one of consistency or availability. So, what this theorem is going to do is say, well, all right, suppose that you can't put a hard bound of 30 milliseconds on the network latency. Then this theorem tells you how much consistency you have to give up, given some network properties, okay, in order to achieve that availability. Right, so think of the banking application, right? Remember I said you've got ATMs distributed around the world, they dispense cash. They'd rather not let the bank balance go negative, but they might be willing to tolerate a certain amount of risk in order to be able to dispense cash even when the network is misbehaving. Okay, it's a business decision there. How much risk do you want to take? This formula gives you explicitly how to handle that risk. It's actually even much more interesting because one of the things that a lot of people are working on these days is mixing embedded computing, edge computing, and cloud computing. Okay. So edge computing is on processors that are close to the embedded system, but are, bolted to the factory floor or something instead of moving around in a robot or something like that. And the cloud is obviously way out there. Well, you have this different latency properties on the network connections between the edge components and the cloud components and the embedded components. Those all become parameters here. And they can be widely heterogeneous. So you can use this formula to guide how you move your computations between the edge, the cloud, and the embedded platforms. Okay, so first of all, in order to put this in a database context, we need to talk about consistency in a rigorous way. And it turns out that in the database world, consistency is a rather subtle idea. I hinted at this already when I talked about eventual consistency. So if all components agree on the order in which updates to a shared variable occurs, right? They agree on the order of the updates, then you have an eventually consistent system because if updates ever stop, all of the components will end up at the same place. Okay, so that's called eventual consistency. There's a more subtle issue, a more subtle problem, which is called causal consistency. And causal consistency becomes a big issue in databases, and it becomes a non-issue in linear function. I'll explain to you why. So first of all, causation is usefully distinguished between two different forms. So you can have an event E1 that causally affects E2 if loosely E2 cannot behave as if E1 had not occurred. Okay. that wording is a little bit subtle and easy to misinterpret. Okay? But if you put it in the context of lingua franca, if a reaction updates a state variable at a certain logical time, and that state variable can affect what some other reaction does, then the order in which these reactions are invoked needs to be specified in order to achieve this causal consistency. Okay. We want that communication through the state variable. There was a different form of causation, which is called counterfactual causation, which is that event E1 counterfactually causes E2 if E2 will not occur if E1 had not occurred. Okay, so in lingua franca, this happens when a reaction produces an output that triggers another reaction. Okay, that's a counterfactual causation relation between those two reactions. And that's not the same as a relation through a state variable, where this reaction updates a state variable, which then affects some other reaction's behavior. So there's a subtle distinction between those. In both cases, we write, we define a causality relation, and we say that E1 causes or has a causal relationship with E2. So let's build a simple process model, okay, where you've got two sequential processes, P1 and P2, and there's 4 operations available. One operation is a write operation, where you can take a new value and merge it with the old value of the variable. Okay, it's called a merge operation more generally because in the database community, it's not always just an overwrite. Okay, sometimes, for example, in a bank balance situation, the merge operation might be to add a value to a balance or subtract a value from the balance rather than just replace the balance. Okay. So the merge operation is updating a local variable. The read operation reads the value of a local variable. The S operation sends the value of a local replica to some set of other processes. Typically, you need to do this after you run a merge. Okay. And then the A operation accepts a new value from some remote place. So let's be concrete. So this picture shows a particular scenario that comes up in a very simple distributed system, a distributed chat application. All right. So W1 is, Joe posts a picture of Sally at a recent party, and he just on his laptop uploads the picture to the app. Okay. Sally posts that her son Billy is missing. Sally's message is sent to Joe's process. Joe's process receives the message. Okay. Sally posts that her son has been found. That message is sent again to Joe. Joe receives that message. Joe reads Sally's messages and sends a message saying, that's good news, that's a relief. Okay. Straightforward sequence across 2 processes. Okay. What happens if we have another observer? So here, Akosh receives Joe's picture of Sally, receives Sally's post that her son Billy is missing, receives Joe's post that that's good news, a relief. Akosh doesn't think much of Joe now, right? I mean, why is Joe happy that Sally's son is missing? Joe only later receives the message that her son has been found. Okay. See the problem? This sequence violates causal consistency. This is exactly the kind of thing that database designers are trying to avoid. Violating this causal consistency because what happens is that Joe's response when Joe posts "that's good news," that's based on a local state update of a shared variable. That local state update was the receipt of Sally's message that her son had been found. That updated the state of the local variable, which is the state of the conversation. Okay, and that affected Joe's response through the state variable. So this is the causal consistency, not counterfactual consistency. Okay. And Joe was able to see Sally's second message when he responded. But Akash didn't see Sally's second message. Okay, just saw Joe's response, which means that the state of Akash's copy of the state variable had a missing element in the causal chain. This is a violation of causal consistency. So formally, the causality relation is the smallest transitive relation between two events, where if E1 precedes E2 in a process, then E1 is causally before E2. Any two events that are in the same process are ordered in this way. Okay? But in addition, if E1 is sending a value in one process to the other is an acceptance of the value, then there is also a causal relationship there. So causal consistency can be put in terms of these relations as follows. So it's kind of a bit of mind-twisting logic there. Right? If you have event W3 is causally before W4, W3 is causally before A6, and W4 is causally before A5, then causal consistency means that we cannot have A5 causally before A6. But that sequence does happen. Okay. This is the violation of causal consistency. So what do you think? Does this occur in lingua franca? Can it occur? Yeah, in fact, the error message that you get when you have a causality loop is in large part because you can't guarantee that this won't occur. So programs with causality loops are rejected. But in addition, you can see that if, first of all, any two events that occur in the same process, they might have different timestamps, okay? Or tags, more precisely, if they use superdense tag. But if they have different timestamps, those will be in order in the process. Okay? If they have the same tag, then there is a causal chain between the reactions associated with these events. And the lingua franca engine guarantees that the reactions are executed in the order defined. That's precisely why the causality loops are rejected. It's because you can have a circular requirement on ordering of reactions. Okay, so within a process, everything is by order. And in addition, as long as you don't use the physical connections, right? As soon as you use physical connections, you have no guarantees. This causal consistency. But without physical connection, the timestamps get transported between components. And those timestamps are respected across the components. And so any update to a state variable will either occur at an earlier logical time, in which case all of its effects have been taken into account by the time you process some later tag event, or they have identical tags, in which case the causal chain relation will enforce the order in which the reactions are. Okay? So lingua franca by construction gives you causal consistency. As long as you don't use physical connections, and as long as you don't get deadline violations or safety process offset violations. Right? Okay, so that's a pretty nice feature because ensuring in a distributed system this causal consistency property, in general, this is really pretty hard to do. And you kind of get it for free from the infrastructure with lingua franca. Notice that this guarantee, however, does not apply to side effects in the physical world. So if you have a reaction that drives an actuator, and another reaction that drives an actuator, and these two things interact in the physical world, if there may be no causal relation between the reactions in the lingua franca, in which case you could violate causal consistency through the physical world. So you have to be really careful. Also, if you add after delays in your connections, you're explicitly asking for orderings to be reversed from what they would be otherwise. Bring it explicit in your program rather than letting it happen by accident. Okay, so this is the terminology that we're working with to develop this theorem. These four kinds of operations. Merge, read, send, and I'm going to go fairly quickly through this because I've given you a pointer to the paper that describes this in detail, and I think it's a little tedious to work through, but I want to give you just kind of a sense of how it comes together. Okay. So first, the definition of inconsistence. So if you have a write event on process J, it has tag G sub J, and G sub I is the tag of a corresponding accept event on process I, or infinity if there is no corresponding accept event. Okay, so let's just parse that sentence, right? So process J updates a variable at tag G sub J. If that variable is sent to another process, okay, there will be an accept event on that other process. And that accept event will have the same tag. Okay. Normally, or if you use after, it'll have a bigger tag, but it will have a tag. Okay. And the inconsistency is the difference between those tags. The tag of the accept event and the tag of the accept event. So this is why when I put in that an after on a connection between two federals, that's explicitly allowing inconsistency because it makes this quality bigger than zero. Right? So the inconsistency between processes I and J is simply the maximum of such differences over a trace of the execution of a program. There's a subtlety here in this theorem, which is that every relation is a statement about a particular execution of a program. Okay, it's a trace-based semantics. In lingua franca, you can think of a lingua franca program always as a specification for a family of traces. Okay, a bunch of possible executions. This statement is about a particular trace. It's the maximum over all update events and the corresponding receive events. Now notice that if G sub I, if G sub I is infinity, right, it doesn't receive the event that J updated. What does this tell us that the inconsistency is? Okay. Right. Process J updates a variable. Process I never receives the update. Okay. Those, with respect to that variable, those two processes have infinite inconsistency. They don't agree at all on the value of that variable. Right? Process I never receives the update. So that's appropriate limiting condition. Okay, does that make sense? Okay, so that gives us a numerical quantity for the inconsistency between two processes. A strongly consistent system is one where the inconsistency is zero for all pairs of processes. This means that they all agree on the tag of any update. There's no after delays on the communications. Okay. That's by definition a strongly consistent system. Okay, we can define the unavailability as follows. So if you have a read event on process I, and d sub I is the tag of the read event, capital T sub I is the physical time at which the read event is processed. In the unavailability, at process I is the maximum difference between this physical time and the tag. How does that make sense, right? This says, for example, think of it from the actuator perspective. You've got this braking system. There's an input with a timestamp to the braking system. The unavailability is the difference between the timestamp of the input and the physical time at which the braking system is invoked. Right? So unavailability is bigger if the physical time is later. That's the latency of the response. Physical time gets large, the unavailability is large. Physical time always gets compared against the timestamp. Okay, so that's unavailability. Lingua franca has to guarantee that events are processed in timestamp order. And in order to do that, it has this feature of having to wait until it can be sure that all the previous events with earlier timestamps have been processed. Right? So we call that a processing offset. And on a trace, the processing offset is simply the maximum difference between the physical time at which an event is processed, a write event in this case, and the tag of that write event. Okay. So this looks a lot like the unavailability, except that it's referring to write events instead of read events. Okay. It's a bit of a subtle point here. Okay, but the write is when you do the update to the state variable. The read is when you read that state variable and drive an actuator. Okay. So the unavailability is about driving the actuator, whereas the processing offset is about preserving the timestamps and not doing a write before you can be allowed to correctly do that write. Okay, that's the difference. And then the last variable we have to define is apparent latency. Okay, that has a kind of similar definition. Right? So if G sub J is a tag of the write event in process J, it's triggered by some external input of J. So T sub J is the physical time, tau of GJ is the physical time at which of that external input, right? Because the external input drives a physical action, it gets assigned a timestamp. That's the timestamp. Then capital T sub I is the physical time of the corresponding accept event on process I, or infinity if there is no such event. So in other words, you have a physical action on one process, J. It gets assigned a timestamp. A message gets sent to another process, and at that other process, then that message is received at a physical time T sub J. Okay. This is the apparent latency, the difference between the physical time at which you receive a message and the timestamp of that message. Okay. So notice that in the braking example, That time increment includes the execution time of the braking assistant software plus the network limit, plus any clock synchronization. Okay. This is the interesting thing about this, is that you can think of this apparent latency as being the sum of 4 clocks. Execution time, network latency, clock synchronization error, and the processing offset. Okay. But the nice thing about this apparent latency is that it's an immediately measurable quantity, whereas none of these three is measurable. Okay. Well, actually, I mean, you can locally measure execution time, but you can't measure network latency. You can't measure clock synchronization error. These two are indistinguishable. Okay, so this is a measurable quantity. And then you can put all these together and just, it immediately follows from their definition, this relation between them, which is that the unavailability is the maximum over all the processes, the processing offset, and the maximum of the apparent latency. Okay. So you get a numerical relation, and notice that it's subscripted by the processes. And so the apparent latency can be completely different between any two processes. This is why this works so nicely for, situations where you're trying to trade off edge computing with cloud computing, with embedded computing. The latencies can be different between any two processes. So this reduces to this rather compact theorem, which is that unavailability is the maximum of the processing offsets and the apparent latency minus your tolerance for inconsistency. And you can see immediately how the CAP theorem, Eric Brewer's CAP theorem, follows from this, right? Because if you have very large latency, your network is broken. Okay. You can either have very large inconsistency or very large availability, but you must have one or the other. There's no way to get both of these numbers to be small if this is large. Right? So the CAP theorem becomes a special case of this numerical relationship. Now, here's where things get a little more mathematical and a whole lot more beautiful. Max plus algebra. How many of you have seen max plus algebra before? Anybody? How many of you have taken a course in algebra? About finite fields and rings and stuff. So, a little more advanced. Yeah. Okay. So cool. So this won't be completely unfamiliar. So max plus algebra is an algebra that has an addition operation and a multiplication operation. The addition operation between two numbers is defined to be the maximum of those two numbers. And the multiplication operation is defined to be the sum. And what the heck is that? Minus psi. It's just the sum. A plus B. Yeah, so multiplication is the sum. So just make sure we understand the algebra. What's the additive identity? Nope. Assume the numbers are integers that could be positive or negative.
Something like minus infinity.
It's minus infinity, yeah. I heard a voice from the heavens telling us the answer, right? Because the maximum of minus infinity in anything is the anything. Right, so the additive identity is minus infinity. What's the multiplicative identity? 0. Right? Okay, so we've got these two operators, and they satisfy all of the nice properties of algebras. The operators, addition is associative. Multiplication is also associative. Addition is commutative. Multiplication is commutative for scalars, but it turns out not to be commutative for matrices, but that's also true of ordinary algebra. So, and multiplication distributes over addition. So if you look at the sum of B plus the maximum of A or B, that's the same as the sum of as the maximum of the sum of A and C and the sum of B and C. Okay. So question? Yeah. Okay, so we've got an algebra, and in this algebra, you can define a matrix. Okay. Actually, we have to step outside the algebra to define the matrix. So the matrix elements are going to be calculated in ordinary algebra. Where the ijth element is the apparent latency minus your tolerance for inconsistency minus the processing offset. And this is actually just cancels out the processing offset that shows up in this apparent latency. So this will actually, the sum here, Lij minus Oj is the sum of execution time, network latency, and clock synchronization. Those three things. So that gets then subtracted, and you subtract from that your tolerance for inconsistency. Notice your tolerance for inconsistency can be different for any pair of processes here. Okay, so you can design a heterogeneous system where you tolerate inconsistencies here and not there. You tolerate unavailability here and not there. Okay. Mix these things up. So then, with that matrix, the CAL theorem becomes a very simple linear format. If A is a column vector with the unavailability of each process, you can write that as a column vector of processing offsets plus this matrix times the processing offsets, or in a very nice linear form, unavailability, the unavailability vector is a matrix times the processing offsets, which includes the inconsistency. Specification for inconsistency. No, sorry, specification for inconsistency. And I is the identity matrix in max plus, which has zeros along the diagonal and minus infinity. So the additive identity is minus infinity, the multiplicative identity is 0. So the identity matrix has zeros on the diagonal. Beautiful, simple linear formula. And if you look in the paper, you can see that there's actually some very nice theorems in the world of max plus algebras, where you can derive properties of this system that are simply determined by this matrix. Solve the system of equations in a very clean and elegant way. Leave that for you guys to read about. The bottom line, the real thing is that it lets you work with these numerical relationships very explicitly. So if you go back to the car braking system, you specify your availability requirements, which are deadlines. You state your requirements on the network. You specify a tolerance for inconsistency. This is logical. And this formula tells you exactly how much availability is rising. So in particular, if the communication latency exceeds 10 milliseconds, right, then the formula tells you that one or the other of inconsistency or availability is going to or unavailability is going to have to go up. You have to pick one. You get to choose to sacrifice availability or consistency. And in lingua franca, you can make that choice currently by just choosing the centralized federation or decentralized federation. And by the way, I should credit Solution for Penny because he's the one who really did pull the oars and implemented these. Okay, so I think we're going to stop there and a little bit early. I